So we have seen linear dependence and linear independence on last time when we started. So if one vector can be generated by multiplying with some number on the other vector, we call those two vectors as linearly dependent. Correlation. Correlation 1 is called as linear dependence. If there is no correlation, we call it as linear independence. If you have too many vectors or too many columns or rows, you want to see whether they are linearly dependent or independent, you need to form a linear combination of all those vectors and see these coefficients. We can say that it is these vectors are linearly independent only when these coefficients are 0. One of those coefficients is non-zero, then we call it as linearly dependent. So this is like simple, right? If you see this, linearly dependent, linearly independent. If you see this is linearly independent. When you combine these two, there is one coefficient -2 into v1 plus v2 is equal to 0. Right? So there are coefficients -2 and 1. Right? So r 1 by 2 on this 0.5 on this. Right? v1 plus 0.5 v2 is also a v1 minus, sorry. So it's also 0. So 1 and -5 are the coefficients there. So it is not needed that a1, a2, a3 are integers. They can be real numbers also. Okay. So that is linearly dependent. How to check? You take vectors, you form a linear combination, you solve those equations, find the coefficients. If all coefficients are coming 0, you say independent. If some coefficients are coming non-zero, you call that as dependent. So I solved those equations and I got some numbers here. So I'm saying it is dependent. Theoretically we wrote the same, and then rank of a matrix we tried to understand. The maximum number of linearly independent column vectors in a matrix are the maximum number of linearly independent row vectors. Whichever is low is called as rank of a matrix. So if you see this, R is a maximum independent row and C is the maximum independent columns. Right? Rank of A is equal to R if R less than C. Right? Rank of A is equal to C if C less than R. Whichever is minimal, that becomes the rank. Independent vectors, row and column independent vectors. Whichever is low, that becomes the rank of the matrix. Screen is changing, right? Screen is changing as and when I'm changing.
Yes, sir, it is good. It is good compared to last time.
Yeah, this is dongle, so it's working well. I connected through phone last. Okay.
Okay.
Okay, so here we try to do the equation solvation thing, right? Here we are solving the equations and trying to find the coefficient. The same thing I am doing using row reduction echelon form. We call this as row reduction echelon form. Basically, we are doing solvation only. We are multiplying. We switched the third column to first column, and then we multiplied the first row with 4 and subtracted from R2. That is nothing but took the first equation, right, multiplied that with some number, and then took the second equation and subtracted one from the another. We have got this one, right, like this only. See this? I multiplied something with the first row and added the third row or fourth row. Then I have got a simpler equation or whatever the coefficient, right? So the same thing we are doing here with the row reduction echelon form, and our goal is to nullify or make some of the rows or columns 0. When some rows or columns are becoming 0, that means they are dependent on other rows or columns. I hope you understand and agree. When a row or a column is becoming 0, that means that row or column is dependent on other rows or columns. Right? So that means we are eliminating the dependent rows and dependent columns. That way we are finding independent rows, right? Independent columns. Maximum number of independent rows and independent columns. In that, whichever is minimum. The count, right? Maximum independent rows are 2. Maximum independent columns are 4. So 2 is the minimum. So minimum of maximum independent rows and maximum independent columns is the rank. So we call that as rank of a matrix. So rank is 2. Okay. So we understood dependent and independent vectors to understand rank of a matrix. So why we are understanding rank of a matrix? If you find eigenvectors or eigenvalues for a matrix, they are going to be equal to the rank of a matrix. The number of eigenvectors and eigenvalues of a matrix are going to be equal to rank of a matrix. So we'll see what is the eigenvalues and eigenvectors in a moment. But we are trying to form a better ground to understand the other advanced concepts. So this is vector multiplication. Right? So it is matrix multiplication only. They are one row, one column thing, right? So it is matrix multiplication only. See this row multiplying this column, you get one number. So vector multiplication is commutative. And then we saw the norm of a vector or Pythagoras theorem, right? So a data point is called as a vector when you try to calculate magnitude and direction of the data point. Right? So this is the length of a vector or norm of a vector, we call it as L2 norm, right? We already used it. And then unit vector. You can make any vector a unit vector. The unit vector is a vector which has got length 1. Right? Length is nothing but norm. L2 norm is 1. So here I have taken V1, V2, but when I try to look at the length of V1, V2, it is square root of V1 square plus V2 square. This we don't know whether it is 1 or not until and unless we see values here. They are 1. No, there are some values here. You can actually say that whether it is 1 or not. But you can make any vector a unit vector by dividing the vector with a L2 norm. V1 by square root of V1 square V2 square. V2 by V1 square V2 square. Right. When now right to this vector, when I calculated the length, it actually came 1. See this? V1 by V1 square V2 square, right? Whatever that square, and then everything got cancelled and you got 1. So any vector you divide with L2 norm, the vector becomes a unit vector. Okay, this point you got, right? So this is going to be used in NLP a lot. And then the projection of a vector, we used this in SVM, right? The V vector is projected onto U, and the length, how much is the projection value you can calculate using this formula. U transpose V is equal to P into the length of a U vector. So P is equal to U transpose V by length of a U vector. Okay, the projection is used, was used in SVM algorithm, but we are understanding this for NLP purposes. We'll actually use, there is a concept called as cosine similarity. There again we'll use these projections and all. Okay, and then diagonal matrix. Right? All the values in the non-diagonal space are 0, and diagonal space are non-zero. Then you call it as diagonal vector, diagonal matrix. And diagonal values are 1. Then you call it as identity matrix. A into I is equal to I into A is equal to A. Right? Any I is like 1 in numbers. In integers are real numbers. You multiply any number with 1, you get that number. Like that, you multiply any matrix with I, you get the same matrix. You know all these concepts. So singular matrix. Inverse of a matrix can be calculated like this: 1 by AD minus BC, D minus B minus CA. This is just a 2 by 2 matrix, so it is easy to calculate inverse, but in a bigger matrix, it's going to be a bit difficult because calculating determinant, it takes a little more effort. So we need to understand what is inverse, and this AD minus BC is called as determinant. For a matrix, if AD minus BC is 0, then you cannot calculate inverse. That is called a singular matrix. So example is this matrix. See, AD minus BC is 0. Divide by 0 error will come when you try to calculate inverse of this matrix. That is called a singular matrix. Symmetric matrix, right? The lower triangle and upper triangle are going to be equal. Distance measure between multiple cities is going to be a singular symmetric matrix. And correlation matrix is also a symmetric matrix. So Aij is equal to Aji. A13 is equal to A31. Right? That's the symmetric matrix. Now eigenvalues, eigenvectors. So to understand this eigenvalues, eigenvectors, we understood all that. Okay. So what is eigenvalues, eigenvectors? We'll understand first, and then we'll look at the mathematics. Eigenvectors or eigenvalues are also referred to as characteristic vectors or latent roots. Okay. These are all, we cannot understand eigenvector, eigenvalue, latent roots, but you can understand this, right? Characteristic vectors. So for every matrix there will be characteristics. Right? It depends on the data. When I say matrix, right, I am not saying mathematical matrix. I am saying data. Data represented in a form of matrix. So if you take correlation matrix, this characteristic of this matrix is correlation. Right? Correlation between different columns. When you actually extract eigenvectors or eigenvalues for this correlation matrix, you will get correlation as the extract or the characteristic. Right? Characteristic vectors. What is characteristic of this matrix? Correlation. Right? If you take relationship between two different cities, right? This cities matrix, right? You have n number of cities, and you took the distances between different cities, and then calculate eigenvalues or eigenvectors. What you get? Essence of distance. Okay, getting it? When you calculate eigenvalues, eigenvectors, you get characteristic vectors or characteristic values. What are characteristic values? What are characteristic vectors? We'll see in a moment. But basically, the matrix you are trying to calculate eigenvectors to should have some meaning. Okay. If the matrix is a correlation between different columns, you find eigenvectors. That eigenvectors will have the strength in the correlation. Okay, strength. Eigenvectors actually represent the strength in the correlation. If the matrix is a distance between different cities, then the eigenvector will have the strength in the distances, right? There may be closer cities, and there may be farther cities, right? So the farther cities will have bigger numbers. So the vectors will actually get that essence into those eigenvectors. Did you get it? The point? Did you get the point, or any questions there? I said characteristic vector, right? Sorry. So let us try to understand a little more, and then I'll start for questions. So in German, eigen means specific of or characteristic of. Right? So characteristic vectors they can say, but somebody from German would have found it and they named it as eigenvectors. Okay, eigen means specific of or characteristic of. The set of eigenvalues of a matrix is uh, also called as spectrum. Okay. They call it as spectrum, but the eigenvalues specify the strength. Okay, we'll see that in a moment. So example of eigenvectors, like characteristic vectors, is principal component analysis. Eigenvectors extract characteristic of covariance matrix. Eigenvalues quantify the amount of essence extracted by eigenvectors. So this is very important point. In principal component analysis, we are trying to understand PCA algorithm. Okay. In principal component analysis, what we do is we take covariance matrix. This is correlation matrix, right? This is correlation matrix. Okay. If you have to calculate correlation between two columns, what we do? If you have to calculate correlation between two columns, what will you do? Do you remember the formula for correlation? So this is covariance, right? Xi minus x bar, yi minus y bar divided by n minus 1, right? So xi is the data point, x bar is the that column's mean, yi is the data point, and y bar is the that column's mean, right? Do you remember these formulas? Or
Yes, sir.
yeah, the correlation is covariance divided by standard deviation of x and standard deviation of y, right? So it's a standardized value. Covariance may vary, right? Vary like it will be like minus infinity to plus infinity. But when you calculate correlation, it's going to be between -1 and +1, right? So in eigenvalues, eigenvectors, we calculate covariance matrix, not the correlation matrix, and then try to extract the essence by using eigenvalues, eigenvectors, decomposition. We call it as decomposition. Okay. So here eigenvectors will get the characteristic and eigenvalues will quantify the amount of essence each eigenvector extracted. It is like this. There may be, there are 1, 2, 3, 4, 5 columns are there. Okay. When you calculate correlation or covariance, if you see this, there is a very strong relationship between uh, experience and salary. Right? Right? Experience and salary, there is very strong correlation, positive correlation. And again, the average behavior score and salary is negative, strong negative correlation. Right? There may be some weak correlation, there may be some strong correlation. But when you extract the essence, right, when you calculate eigenvectors, the eigenvectors will actually extract, eigenvectors will be 5, but the first one will get more essence, second one will get less essence, third one will get even lesser, fourth one will get even lesser and even lesser. Which one got more, which one got lesser can be identified by eigenvalues. Okay, eigenvector will extract the essence. Eigenvalue will specify how much essence each vector actually extracted. Okay, by end of the session, right, we'll understand. So if you understand this concept, right, PCA will be very easy. Okay. Basically PCA only we are trying to understand. So eigenvectors and eigenvalues are vectors and numbers associated with square matrices, and together they provide the eigen decomposition of matrix which analyzes the structure of the matrix. This is important. So basically we are trying to decompose, or it is like this. We have seen sugarcane, right? Sugarcane juice. If you get 10 sugar canes, you put it into the sugarcane machine and you squeezed maybe 5 glasses of juice, okay, or 10 glasses of juice. You cannot distinguish which glass is actually extracted from which cane, right? Out of 10, which glass extracted, the how much each glass is having of each different sugarcane, like that. So when you apply eigen decomposition, it will take the whole matrix, squeeze it, right? Extract all the essence out of those sugar canes or the columns and put it into glasses. Okay, but we'll see that in a moment. I think my analogy may be a little odd, but that's what it is. So in theory, if you take a vector, right, if you take a matrix A and multiply that with a vector x, and if you take a constant and multiply with the same vector, if both are giving you the same result, then you can call that x as an eigenvector and lambda as an eigenvalue. Okay? In mathematics, you take a matrix, multiply that with a vector, and take the same vector and multiply with some number. Right? If you get both same result, then you can say x as a eigenvector of A and lambda is an eigenvalue of A. Okay, let us see. See this here? I have taken a matrix 5, 1, 3, 3, and then I have taken a eigenvector, eigenvalue. I think I should. It's a mistake. Value it is. But eigenvalue lambda is equal to 6. I multiplied A into x1. I've got 6, 6. Okay. I multiplied lambda 1 into x1. I've got 6, 6. See, the right hand sides are equal. So I can say ax1 is equal to lambda x1. Okay. So this 1, 1 is an eigenvector for this matrix. The 6 is an eigenvalue for this matrix. There are 2 columns, right? And one more important point is eigenvalue, eigenvector decomposition can be done on a square matrix only. There are 2 rows and 2 columns. So we will get 2 eigenvectors and eigenvalues. So this is first eigenvector, this is first eigenvalue. This is the second eigenvector. When I multiply the 5, 1, 3, 3 with the eigenvector 1 minus 3, or 2 minus 6. Okay. And then I have multiplied this 1, 3 with 2, 1 minus 3 with 2, 2 minus 6. So right hand sides are equal, left hand sides are equal. So you can say this is another eigenvector and this is another eigenvalue. Okay.
One question, sir. Vector x2, x1 and x2, they are something different than matrix A.
Basically, we decomposed this matrix into 2 eigenvectors and 2 eigenvalues. Okay. So how do you know that this 1, 1 is the eigenvector and 1 minus 3 is the eigenvector? We'll see that. How to derive eigenvalues and eigenvectors mathematically, we'll see in a moment. Okay. But yeah, go ahead. Go ahead, sir. Any question?
No, sir. I just wanted to know how they were arrived at. But anyway, you said you will.
Yeah, we will actually. We'll see in a moment. I know how we will actually find how to find these eigenvectors, eigenvalues. I'll show you in a moment. Okay. So we can represent the eigenvectors as a matrix like this: 1, 1, 1 minus 3. See this? This is 1, 1. This is 1 minus 3. 2 vectors, right? I join those 2 vectors and create another matrix. Eigenvector matrix it is. So eigenvalues also will create a matrix like this. Lambda 1, 0, 0, lambda 1. It's a diagonal matrix. See, lambda 1 is 6, lambda 2 is 2. So we kept those. So maximum bigger value will come first and smaller value will come next. Okay. Similarly, the bigger values, the bigger eigenvalues vector will come first in the eigenvectors matrix. See, this 1, 1 is the first matrix, 6 is the first value. Okay, 1 minus 3 is the second matrix, 2 is the eigenvalue. Like this, you need to form. After finding the eigenvectors, eigenvalues, you need to follow this convention. Okay, so the first bigger value will come first, and the value associated with the eigenvector will come as the first column in the eigenvector matrix. The value associated with the second value will come in the as the second matrix. If you have more, right, you will get more. On a two-dimensional matrix, it is easy to show. That's where I took a two-dimensional matrix. See this here, AV is equal to V lambda. What is lambda? Lambda is the eigenvalues matrix. V is the eigenvectors matrix. A is our original matrix. See this A. This is A. Okay. This is V, eigenvectors matrix. We multiplied these two. I got 6, 6, 2 minus 6. Right. And then I have taken V and I multiplied with lambda. Right. This is the lambda matrix. I have got 6, 6. No, 6, 2, 6 minus 6. So right hand sides are equal, left hand sides are equal. See, AV is equal to V lambda. So this is same thing, right? If you see AX is equal to lambda X or AV is equal to V lambda, both are same. We just formed them as a matrix and then I am trying to multiply that. Okay. The point we are trying to understand here is AV is equal to V lambda, right? If you multiply both sides with V inverse, you get A is equal to V lambda V inverse, right? So basically what we are trying to say is a matrix A can be represented as this, then you get V and lambda, right? V matrix and lambda matrix can be found if you can decompose this A into V lambda V inverse. Okay, this theory this is. So how to find V lambda V inverse? I'll show in a moment. But A can be represented. A can be derived by multiplying these three matrices like this. Okay. This is called as eigenvalue decomposition. This process is called as eigenvalue decomposition. So let us look at how to find these eigenvectors and the eigenvalues. Okay. We have seen what are eigenvalues and eigenvectors. They are characteristic vectors. Eigenvectors represent the characteristic of a matrix. Eigenvalue quantifies the how much essence each matrix extracted. Let us see what that means is. We have 5, 1, 3, 3, a matrix, right? And I decompose that into 1, 1 and 1 minus 3, two vectors, and 6 and 2, right? So here, the 6 says that this vector extracted a maximum amount of essence from the matrix. This vector extracted a little less amount of essence from this
Screen
matrix.
hand, sir.
Oh, really?
Yeah.
Let me start sharing and start. Is it visible now?
Yeah.
So now here, if you take this matrix 5, 1, 3, 3, right? We decompose that into 1, 1 and 1 minus 3, right? These are eigenvectors. I said they are characteristic vectors. And then eigenvalues actually quantify the characteristic, right? So it is like this matrix can be decomposed like these two matrices, but the first vector has extracted more essence and the second vector extracted less essence. How much essence each vector extracted can be found by the eigenvalue. Right? If this matrix is a covariance matrix, right, most of the covariance was extracted by the first matrix, and a little less covariance extracted by the second matrix. Did you get that point? If this is a covariance matrix, this vector extracted more, this vector extracted lesser. How did I know? By looking at eigenvalue. the eigenvalue associated with this vector is bigger compared to the eigenvalue associated with this vector. So I can say that this vector extracted more essence compared to this vector. Got it? That's theoretically you need to remember these points, and we'll see how to extract those eigenvectors and things. Got it? So now, right, how to find out eigenvalues and eigenvectors? Suppose that this is the matrix. Okay. We said that A into X is equal to lambda into X. So for at least one non-zero X and lambda, if it is zero, right, everything will become zero and anyway going to be equal. But if lambda and X are non-zero, we said for A there is a eigenvector X and a eigenvalue lambda, right? If we say this, we can actually represent this like this, right? Ax minus lambda x is equal to 0. Okay. For to take the x the vector as a common thing, right? I am multiplying the lambda with I. You know I, right? I is the identity matrix. Okay. Now I took x as common here. Okay. So I converted this equation like this. Okay. Suppose that, right? If you suppose that there is an inverse for this matrix. Is that a matrix? The highlighted part, is that a matrix? A minus lambda I, is that a matrix? Yes, no. A minus lambda I, is that a matrix?
Yes, yes.
If there is an inverse for that matrix, and if you are multiplying with inverse on both sides, see this here, if that matrix, so if that matrix is invertible, what happens? If you multiply using inverse on both sides, right, you will get 0. I think I should have put inverse on this side. That's okay. Right. So if you multiply, right, what happens? This a minus lambda I into a minus lambda inverse will become 1. Then it is saying x is equal to 0. Right. If there is inverse for this matrix, then it is it is saying x is equal to 0. X is a we said it is a non-zero, right? It's a non-zero vector, right? And then when you actually have an inverse for this matrix, you are getting 0. That means A minus lambda I should not be invertible. If you have to find a non-zero eigenvalue eigenvector, A minus lambda I should not be invertible. Did you get that point? If you have to find a non-zero eigenvalue and eigenvector, A minus lambda I should not be invertible. Did you get that point? Yes, no. Can I move on?
Yes, it means the determinant is 0.
Determinant is 0. A minus lambda is determinant is going to be 0. Okay. So using that, right, we are going to find lambda. So, right, if we are trying to find a non-zero eigenvector and non-zero eigenvalue. Where I am trying to find non-zero eigenvector and non-zero eigenvalue, A minus lambda I should be non-invertible. It should be a singular. Okay. So when it is a singular matrix, the determinant of the matrix should be 0. What is the determinant of the matrix? A minus lambda I calculated here. A is 5133. Right? This is 5133. Lambda, we want to find that. And then I 1001. Right? So I calculated determinant of this. What is determinant? AD minus BC, right? AD, right? A into D, right? This is it. Minus B into C. That is the determinant. This is the determinant. I calculate this. I am saying this determinant is 0 for this matrix. A minus lambda I, this determinant is 0 because we are trying to find eigenvalue and eigenvector. Right? To find eigenvalue, eigenvector, the basic condition it should satisfy is A minus lambda is 0. So I actually equated it to 0. When it will become 0? When lambda is equal to 2 or lambda is equal to 6, it will become 0. This lambda square minus 8 lambda plus 12 will become 0 when two values, right? Lambda is equal to 2 and lambda is equal to 6, it will become 0. So eigenvalue 2 and eigenvalue 6 we have found. Right? In this, for this matrix, there are two eigenvalues. One is 2 and the other one is 6. How did we found? A minus lambda is equal to 0, or determinant of A minus lambda is equal to 0. Using that, we found this. Okay, using this, right, we are going to find eigenvectors also. Okay, so let us take the lambda is equal to 6 and lambda is equal to 2 and substitute into this equation. So here ax is equal to lambda x, right? And we brought this as, to the other side and we got this equation. In this equation, we will substitute lambda values and find the eigenvectors. See this here? A minus lambda 1 I into x1 is equal to 0. But what is lambda 1? I have taken 6 as the lambda 1. Right? And then we know A, we know I, we don't know x1 and x2. Right? X1, I actually kept 1 and 2 here. Right? So I multiplied this. I've got x1 is equal to x2. I can take any value. 2, 2, 1, 1, 3, 3, 4, 4. Right? Anything is a eigenvector there. But no, we'll take the 1, 1 there. Right? So, and for the lambda 2 is equal to 2, I substituted the values here. A minus 2 into lambda I, sorry, minus 2 into I into x2, right? X2 values I'm finding. So this is the equation. So I substituted x2 is equal to some number 1 and x2 1 is equal to 1. Then I've got 1 and minus 3. This is how we find the eigenvalues and eigenvectors. Any questions here? Any questions?
So here the eigenvectors for the eigenvalue 6 is unlimited, or we will consider only the minimum value.
Minimal ones, right? The basic ones we will consider. But when you look at the equation, right, it looks like you can take 2, 2, 3, 3. But the basic ones will. So here, right, that's what I said. A matrix will have the rank number of eigenvectors and eigenvalues. Rank of a matrix is the number of eigenvalues and unique eigenvalues and eigenvectors. You remember that, right? Got it? So that is the eigenvalue eigenvector decomposition. Right? So now if you look at this, right, this is eigenvector, this is value. So I said this vector has extracted more essence by looking at the value. But that point is very important. So now if we want to look into principal component analysis, right, it becomes easy. Singular value decomposition I'll explain later. First we understood eigenvalues, eigenvectors, I hope. And we'll go into principal component analysis and understand that and come back to this. This PCA will take at least 1 more day, but let me start it, okay, at least. Basically, what is principal component analysis? Right? Principal component analysis will try to extract the essence from the matrix, from the data. What essence it is trying to extract? Covariance between the columns is what it is trying to extract. Okay. So if you take the example here, suppose that this matrix is a covariance matrix. Okay, how to calculate covariance? We know that, and I'll show you in a moment. If you think this is a covariance matrix, and we found eigenvectors and eigenvalues, so this is a maximum covariance. This is the minimal covariance extracted from this matrix. If this matrix is a 100 by 100 matrix, then you will get 100 eigenvectors and 100 eigenvalues. Each value will denote how much essence each vector extracted. Got it? So, I think PC have notes here. So this is the dimensionality reduction. Theoretically, we will understand today, and know how to do it practically. We will see tomorrow. There is a concept called as curse of dimensionality in machine learning. Basically, in machine learning, right? Not in deep learning. If there are too many columns, the model will not work, or the hardware we have will not support, or even in deep learning, it becomes very cumbersome or time consuming to train the model and understand. Okay, many machine learning problems involve thousands or even millions of features. We'll see them, right? In NLP, we'll see them. Right? Thousands of features at least we'll see for training. Not only does this making training extremely slow, it can also make it much harder to find good solution. When there are too many columns, right? You don't know. No, the algorithm will actually try to decide the importance of features and all that, right? So you don't know, maybe it is finding the best one or not, right? The problem is often called as curse of dimensionality. This is for definition purposes. Okay. We'll use dimensionality reduction to reduce the number of columns and try to build a model. The major point we need to remember is when you take a 10,000 or I think 100,000 column data set and trying to reduce it to 100 columns, you should make sure the essence of the data should not be lost. Right? So it is not like you are going to eliminate some columns and take them. In our initial linear regression assumptions, we understood that the multi-collinearity, right? Multi-collinearity is going to be there. There are many columns and they're all correlated between themselves. If you try to eliminate one column, the model accuracy may reduce. But you know that there is correlation, there is relationship between those two columns, right? So they are like 90% correlated. Okay? When you calculate correlation coefficient between x1 and x3, you got 90%. You know that they are strongly correlated. You try to eliminate x2, build a model, the accuracy reduced. No, you thought like, keep the x2 back and x3 out and build a model, you got less accuracy. That means both are important, but the essence is important, right? The essence in both of them is important, but both may not be important, right? Both may not be, we may not need both in the data set. Are you getting the point? So there should be a middle way, right? You extract the essence from both the columns and create one column that's going to reduce the dimensionality, right? That can be done with principal component analysis. Right? That can be done with eigenvalue decomposition. Okay, so if x2 and x3 are correlated, 90% correlated, right? And you cannot eliminate one column and build a model and get the same accuracy as the original data. But if there is a way to combine those two columns or squeeze the essence from those two columns and create one column and get the same essence, get the same accuracy, that's going to be better, right? So the eigenvalue decomposition can do that. You take the columns and extract the essence, use that essence to build a model rather than the original data. Okay, you take sugar canes and squeeze the juice out of it and use it rather than using the sugar canes directly. Right? That's the kind of thing we are trying to do. What is the essence there? We are trying to extract the covariance. A principal component analysis will extract the covariance essence. That means what you need to do, you need to take the original data and create a covariance matrix, apply principal component on top of it, and get the essence. Got the point? Any questions on the concept I explained so far? Any questions?
Sir, one question. So basically here as an example, we want to take away 2 columns and put the essence as a single column. So there will be a reduction of 1 column. Just an example.
Yeah, it's an example. It's an example. Yeah, we will do it for all the columns now. Yeah, it's an example.
Okay.
So, the manually eliminating columns is not a right approach. You should be able to extract the essence and use it so that the data importance, the data's essence is not lost while building a model. So that is called as dimensionality reduction. This is one technique to reduce the dimension. There are other techniques also, but this is mostly used and mathematically a little complex, so I am explaining this. Okay. So I have taken 100,000 features and can be reduced to 100 or 1000. Okay. So this happens at a cost of losing some information. Whatever technique you use, whether it is PCA, right, whatever technique you use, whatever algorithm you use, while reducing the essence, reducing the dimensionality of the data, you will lose some information. So whenever you take a data set, try to use the whole data and build a model first and see how it's working. Then apply the dimensionality reduction technique and see how it's working. Right? First time you built a model with whole data, you got 90% accuracy. You did PCA, you applied PCA and built a model, you got 80% accuracy. The principal component analysis did not extract the essence correctly. So better use the original data rather than the extracted data. No. I built a model and I got 90% accuracy and then I applied PCA. Now I got 89% accuracy. Yes, we can use PCA to reduce the dimensionality and build a model. So it is always suggested to use the original data rather than reducing dimensionality and try to use it. But this is a technique that actually helps you in retraining. Right? First time you built a model, you found 90% accuracy. Then you applied PCA, built a model, 89% accuracy you got. 1%, that's okay because it is going to save lots of the time and processing power, right? The memory processing power and all that, right? So from next time onwards, you directly apply PCA and try to train the model or predict the whatever, right? Whatever you want to do. Okay. And the other thing is the dimensionality reduction technique is an unsupervised technique. If you see this, right, I took all the 100,000 input columns and reduced them to 100 columns. I am not actually looking at the y variable. When you are doing something, while doing something, you look at y variable and try to do it carefully. That is supervised, right? When you are actually trying to use linear regression or logistic regression, right? All those SVM, it is always trying to look at y variable. Am I doing right or not by looking at y variable? How are we able to look at y variable and deciding in the supervised algorithms? What is the basis there? What is it always trying to check whether the model is working good or not while existing the model?
Predicted value
predictions.
Sorry?
predicted value.
Predictions, right?
Predictions, but what is that equation which is actually trying to make the model aware that it is going in a right direction or wrong direction? Cost function, right?
Yes.
Right? Cost function is the one which is actually always trying to keep the model on track, right? But here it is not looking at y value. It is just taking the input and trying to convert it to something else. So this is called as unsupervised learning technique. Okay, I'll talk about the drawback on this unsupervised technique in a moment. So that's where I'm trying to build ground there. So this is the point, right? So you dimensional direction, you take big data and try to reduce it to columns. You reduce. Okay, but you need to remember that you need to take the original data and build a model before you reduce it. Until and unless it is not possible. If it's not possible, your hardware is not at all supporting, then you apply the dimensional direction and build a model. Okay, so let us understand what is how principal component analysis works. So the point is, we have a big data. We are trying to reduce the number of columns so that the model building activity becomes easy. So PCA algorithm works or helps you reduce the dimensionality. So how PCA reduces the dimensionality? Okay. So principal component analysis is one of the projection learning algorithms. You call it as projection learning. What is projection learning? Take this. These magenta dots are, the violet dots are the original data. And we projected those data onto this line, this green line, right? And then we took another orange line. How did we took and what are we doing? I'll explain in a moment. And projected the data onto orange lines also, and then rotated the whole thing. Okay. Now we got these are the new data points. So original data points are those. Whatever the essence in them, we extracted and brought them into these dots on the axis. So that is PCA. Okay, that is principal component analysis. So let us see step by step. We'll see that. PCA finds the principal components of data and transforms data using these principal components. First it finds the principal components. These green line and the orange line are called as principal components. Okay, so if I have to talk in terms of the eigenvalue, eigenvector decomposition, right? These are eigenvectors. This green line and this orange line are the eigenvectors. PCA first finds the eigenvectors and then it projects the data onto that eigenvectors and rotates them. Okay. Principal components are the direction where the data has the most variance or the direction where the data is most spread out. If you see the data, in which direction the most variance correlated, in which direction the data is correlated, on the green direction or the orange direction? If you look at this data, can you see? It's visible, right? If you see the data, in which direction it is correlated, strongly correlated? Green or orange?
How to say that, sir? How to say that it is strongly correlated or not? Please, I don't know.
Okay, so anybody else? When you look at scatter chart, right? Scattered plot, when you look at scattered plot, you can understand whether data is strongly correlated or not.
Yeah, it is denser on the orange line. It's very close to each other.
No, sorry, don't look at the orange line. Let me try to show this. Yeah, this one. This diagram. This is the original data. Sorry. I would have shown this. This is the original data. Suppose that there is a green line and orange line. Green line in this direction and orange line in this direction. Which direction the data is strongly correlated?
Green line.
Green line, right? When data is strongly correlated in that direction, it will form a straight line, right? If you take 1, 1, 2, 2, 3, 3, like x is 1, y is 1, x is 2, y is 2. X is 3, Y is 3, X is 4, Y is 4. It will form a straight line 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Strongly correlated. Same value, right? X and Y have got same value, right? Got it? Got it right? Can I move on? So in this direction, right, it is strongly correlated. This is ultimate, this is like, it will find the direction in which the data is strongly correlated. First it will find the green line, okay, and then it will try to draw, it will draw a perpendicular line to that green line, right? There are two variables here, right? X1 and X2. That's where we get a two-dimensional plot. If there is third variable also, you will have X3, right? That is Z, and there is that principal component is going to be perpendicular to the green one and orange line. For these two, there will be another perpendicular line if you have another variable. If you have fourth variable also, that variable's PCA, principal component is going to be perpendicular to these three, principal components. Getting it right? First, it will find the green line in the direction in which the data is most strongly correlated, and then does the perpendicular line, right? And then perpendicular, and then perpendicular, like that. It is going to find the principal components. Got it? Okay. So we'll talk about assumptions and all that later, but let us see. So this is how it starts. Principal component analysis, right? Original data, this is. Okay, then what it does is it actually centers the data. You take this data set, you see the dots are a little up, right? I centered the data, they came a little down. What is centering? It takes the mean of the first column and mean of the second column and subtracts it from each of the column. Did you get it? What is centering data? See this here? This is the original data. X1, X2, X3, X4, X4, X5. Okay. In diagram, I am showing only X1, X2. Okay. In this matrix, right, I am showing 5 variables. This is mean centering. X1 minus X1 bar, X2 minus X2 bar, X3 minus X3 bar, X5 minus X5 bar. Right? Got it? This is original data. This is mean centered data. Okay. We just adjusted it a little bit. And then it will find the most correlated direction. Okay. So that is the first principal component. First principal component will extract the most essence. Okay. The direction in which the relation is strong, in that direction it will actually find the most essence. This is, for this principal component, right, the eigenvalue is going to be high. For this eigenvector, the principal component is nothing but eigenvector. And for this eigenvector, the eigenvalue is going to be high. Okay, first it found this, and then it actually projected the data onto that, right? It is doing a perpendicular projection. Okay, if you take linear regression, right, it is going to find value here. For this point, the prediction is going to be here. But here it is not prediction, it is actually projection. Okay, so it is a perpendicular projection. All the data points are perpendicularly projected, okay, onto the first principal component. And then the essence is actually captured. So symbolically, I am trying to show this is a violet dot. The violet color got extracted and moved onto the principal component. The color reduced. Okay. Then it finds the second principal component, which is perpendicular to the green line. Okay, the green line exactly perpendicular. It will find the second principal component. and then it will project the data points, the same data points, the original data points onto the second principal component also. Right, when it projected, right, it found those data points. Okay, and then it will extract the essence from the data. The magenta color all gone and the circles became white. Okay, the data points became white. Then it rotates. Why it rotates? I'll explain in a moment. Okay.
Sir,
Before
we go there, can you tell us for the initial data how the points were drawn? Can you please tell us that for the initial data?
This one?
Original data.
This one?
Yeah. Compared to your input data, you have a matrix, right? So from there, can you take an example?
No, don't look at that matrix. There are 5 variables here. I'm showing only 2 variables here, x1 and x2.
Okay, fine. Even for x1, x2, how these dots were put in, can you please explain that? Which is x1 and which is x2 coordinates?
This is x1, this is x2.
Oh, okay.
You can take anything, right? 9 and 6 is the data point here.
Okay. Okay.
This data point is 7 and 7.
Okay.
Right? This data point is maybe around 6.9 and 4. This data point is 5 and 2, right? Like that.
Okay, thanks.
I took mean and centered it. I subtracted mean from x1 and x2. So the data points actually moved a little downward. Right? And then I found the principal component, an eigenvector. Okay? And then projected. And found the second eigenvector, projected. And then rotated. I'll show why I am rotating in a moment. Right? Now, the original data we will not consider. Right? Now we take these data points. Right? The values on the x-axis and the values on y-axis, we take them as the columns. Right? That is called as principal component analysis or the dimensionality reduction technique. Let me try to draw this a little bit and explain. And after explaining this, right, I'll stop and tomorrow we'll start with the same thing. It takes time. For you, it takes a little time because you need to engulf it, right? So give me 1 second. Take out the time. Hope you are getting it. The concepts I am explaining are really important. The ones which are not important, even though the articles writes them as a big thing, I am not going to talk about them like SVM. It is not that useful.
So principal component first means so first it will look into more correlated values, right?
No, I'll talk about that. I'll talk about it. First, let me cover this whole thing. Tomorrow, day after tomorrow also, we'll talk about PCA only. There is kernel PCA. You need to understand this concept and all that, right? So by Wednesday, you will get complete clarity. If not, right, we'll stop for discussion. Even in between also we'll do, but by looking at your question, right, I think we need to understand more. Maybe I'm wrong, but so here, let me try to show this. So I said that let me take a screenshot of this one also. So I said that this data point is 9, 6. Right? This data point is 7, 7.5. This data point is maybe 6.9, 4. Right? Like that. Okay. So now when I actually did the eigenvalue decomposition, or I found when I did the PCA, principal component analysis, that actually the data is like this. Let me go back. So the data is like this: x1, x2. We are not considering y. We are not worried about the y variable. Okay, because PCA is an unsupervised learning technique. Okay, so the values are like this: 9, 6, and then 7, 7.5, 6.9, 4, like that the data is. Okay, this is the original data. Okay. Now when I apply PCA, right? When I apply PCA, I pass this data to PCA. Again, I will get new columns, 2 new columns. What I said, this is like sugarcane, right? This is sugarcane 1 and sugarcane 2. I am putting into a crusher, right? I will get the extract. Now when I put it into a crusher, right, I will get extract. The extract is called as Z1 and Z2. The extract is called as Z1, Z2. Some values you get. So why am I saying X1, X1, X2 you put into a crusher, you got Z1, Z2 because it mixes up everything and brings out the essence only. And after looking, after taking the essence, right, you may actually take only, if you have, suppose that there are, here I have taken 2 only, but if you have X3, X4 and so on, Xn, right? After putting it into the PCA, you may take Z3, Z4 only. There may be 100 columns in your data, original data, but you may take only till Z4. It depends. How many to take? That's a big question. Okay, I'll answer that. But when your original data is passed into a crusher, the PCA, you get a new column set. Altogether new column set. It's an extract. It may have mixed all the data and found out this. Did you get that point? From that mixed up data, you may take only 4 columns. Out of 100, you may take only 4 columns. That is dimensionality reduction. Your original data is 100 columns. After applying PCA, you took only 4 columns. How did you come to know that 4 is enough? I'll talk about that later. But that is called as dimensionality reduction. When you apply PCA, your original columns will not stay the same. You get new, mixed up data, which will have the essence. Okay, that point is clear. That point is clear. Can I move on?
Yes, sir.
Okay. So let me explain that now, right? So here, right, I took the original data, centered it, then found out the first principal component and projected the data onto it, found the second principal component, projected data onto it, then rotated, right? So if you look at this carefully, if you look at this diagram carefully, so original data point here is, right, after centering it, right, the data point actually is 3.5 and 4.5, right? This is original data point, or after centering it, it is 3.5 and 4.5, right? When I projected it, what it became? 4.5, 3. Do you agree? When I projected it, what it became? This original data point, right? Actually, x1, x2, or x1 minus x1 bar, and x2 minus x2 bar. Okay? This is 3.5, and this is 4.5. Okay. When I actually took the first principal component and projected it, the same data, right? The same data became like this: 4.5 and 3. Okay, so that is our first principal component. Okay, so let us go back to the diagram again. So on the second principal component also we'll take the same data point. Right? This data point we have taken, right? So the same data point we'll take. So here this data point, right? 3.5, comma 4.5, right? So when you projected this data point onto the second principal component, what it became? Sorry. The data point is like 1 minus 1, comma 1.5. Okay. When I took the data point and projected it onto x-axis, sorry, first principal component, PC1 I will say, right? This is PC2, right? On the first principal component when I projected it, I have got 4.5, comma 2. I think 3, I think maybe 3, right? And on the second principal component, minus 1 and 1.5. For the same data point, I have got, right, 2 x's and 2 y's. Do you agree? What I am trying to do? I am trying to pass x1, x2, right, into PCA, and I am trying to generate z1 and z2. Right? I am passing this data and trying to produce this. But when I passed 3.5 and 4.5 on the PC1, I have got 4.5, comma 3, right? On PC2, I have got minus 1, comma 1.5. Right? For this data, for this x1, I have got 2 x's. This is 1 x and this is another x. For this y, I have got 2 y's. Got it? This far we are clear? Can I move on? Can I move on?
Yes, sir.
Yeah. Now rotation. Why rotation? Right? I am trying to explain why rotation. So now, where is it? For the same data point, we have got 2 data points. So to make them 1 data point, we'll rotate it. When I rotate it, what happens? When I am rotating it, what I'm doing? I'm actually, the whole thing is fixed. The whole thing is fixed, and we are making this this orange line and red line as x-axis and y-axis. That is rotation. Whole thing is fixed means none of those data points will move. Right? They are all stuck there, and then we are actually rotating it. See this here? The distances between the projections and the data points will not change. Right? Carefully observe that. The distance between the data point and the projection will not change even after rotating. See that? See that? Do you observe it? Right? Rotation is done very carefully. Right? Rotation is done. Basically, what we are doing is the principal components we are making them as axes. Now what happens? Let us see. So for that same data point, right? I think this is the data point. Right? Let me put some numbers here, right? So 4.5 and 3, right? Now what happens on the x-axis? This may be 4, comma 0, comma, sorry, on x-axis 4 and y-axis 0. For the same data point here, x0 and y may be 3. See that? This 4.5 became 4 and 3 became 3. Got it? This data point now got only 2 values. For x1 value for y one value, for x2, for x1 one value, and for x2 y one value. This is called as z1. This is called as z2. Right now, 4.53 x1 x2 have got converted to z1 z2, where z1 is 4, z2 is 3. Got it? Projection part is okay, but if you don't rotate, right, you will get for x1 2 values, x2 2 values. When you rotate, right, or make the principal components as axes, you get only 2 values. Right? For x1 one value, x2 one value. So that is how the PCA works. PCA is actually trying to project data onto the strongly correlated direction, right, and then rotating the axis to generate the new data, squeezed or extracted data. Okay, got it?
Sir, here I did not see any reduction because there is x1 and x2, and we also got again z1 and z2. What is the reduction here?
So that's a good question. So when you apply PCA, you get same number of columns. Right? If you have 100 columns, you apply PCA, you get 100 columns. But we will choose, right, how many to use, right? The one point I was explaining when I was explaining linear algebra was that the first principal component has got 6, right, the eigenvalue. Second principal component has got 2 eigenvalues, right? That means the first one has got more essence, second one has got less essence. If you have 100 principal components, right, in those 100, right, 10 will have the lambda values, the eigenvalues, a number greater than 0, or number greater than 1. The rest of these principal components, right, will have an eigenvalue which is close to 0. That means those, from 11th onwards, the eigenvalues are kind of close to 0. That means those vectors did not capture anything important. So you can eliminate those. You can take 10, z1 to z10 only. Got it? Got it? No?
Yes, sir.
Yeah. So I'll talk about that tomorrow. So basically, how many to choose? I'll show you in the code. By running a code example, I'll show you. Okay. So that is for today. And if you have any questions, I'll answer. If not, right, tomorrow we'll start with the same thing and go about it for maybe around 20 minutes because this is important. In image processing also they used to use PCA, but now with CNN, right, extensively use CNN and GPUs and all that, we are no more using the PCA. We'll use CNN. Okay.
Sir, actually,